Let's now talk about solving recurrences. So we are given a recurrence relation like this. We need to find the value of Tn. There are multiple methods to solve recurrences, like there is master method which requires us to remember a formula and works only for a particular form. In this video, we are going to talk about recursion tree method, which is a general purpose method, does not require us to remember any formula. However, in some cases, this recursion tree method does not give you the exact bound, gives you an upper bound. And this method is very close to programmers. As a programmer, we most of the time draw the recursion tree and we feel comfortable writing the recursion tree. So what we do in this method is, we draw the recursion tree and in the recursion tree nodes, we write down the amount of work done in every function call, right? And at the end, we compute the total work done in the whole recursion tree. So say if I have drawn this complete recursion tree, I just need to count the sum of all node values. So what we do to compute the sum of all node values, we compute the sum of this level, then this level, then this level, and we find the pattern and we find sum of whole series. That's what we do in the recursion tree method. How do we draw this recursion tree? So these are the steps. So if you see the recurrence relation that I have here, we have a recursive part here, right? There are two recursive calls and then we have a non-recursive part. This is non-recursive part and this is recursive part, right? So what we do is, we write the non-recursive part as root of the tree first. Then we write the two recursive calls. There are two recursive calls here, that's why I've written two. If there were three, we would have written three. If there was one, we would have written one. Then there are two recursive calls, so we write those two children here. Then once we have drawn this recursion tree, we further expand these calls, right? And how do we expand it? This is the recursive call for Tn by 2, right? Tn by 2 means it's going to have 2Tn by 4 plus Cn by 2. If I put n equal to n by 2, I'll get 2Tn by 4 plus Cn by 2. So in that, the non-recursive part is Cn by 2. So I write Cn by 2 and I write the recursive parts here. Then Cn by 2 and recursive parts here. See, we need to compute the total work done. How much work we are doing here? Cn. And how much work we are doing here? Cn by 2 plus Cn by 2, which is Cn. You might have guessed the pattern now, right? As soon as you find a pattern, you guess the pattern, you can stop drawing the recursion tree. I have drawn one more time for more clarity. So next time we are going to have Cn by 4, Cn by 4, Cn by 4, and you have 4 Cn by 4, so you have total work done again as Cn. And at the bottom level, you will have CCC and you will again have Cn. So you are doing Cn work at every level. We just need to find out how many terms the series has and we just need to add Cn those many times. So the total work done in this recursion tree is Cn plus Cn plus Cn and the last term is also Cn, right? Now we just need to find out how many terms we have. So what is the height of this binary tree? Can you find an expression for height? You can take some examples. For example, if n is 14, what will happen? You will have 14, then you will have a child with value 7, then 3, then 1, right? So how many levels we have? 1, 2, 3, 4 for 14. And how many levels we will have for 15? Again 4. For 16, we will have 5 levels. So it's coming out to be around log n. And when we talk about asymptotic analysis, we do not care generally about 1 plus minus, right? As long as we know order of growth is log n, we consider log n. And if we just want to find out the exact value, see, let's do one more example, 4, 2 and 1. So how many terms we have for 16? We have 5. It's mainly floor of log 2n, right, and plus 1. Those many terms we are going to have in the series. So if n is 14, then floor is of log 2 base n is 3 and 3 plus 1 is 4. If it's 16, then we have floor as 4 and we have plus 1, 5. So that's the number of terms and you can write it as theta log n, right? We don't need to care about floor, ceil and plus minus. So we have theta log n terms, right, in total, and every term is having value Cn, right? So how much is the sum of this whole series? It's clearly theta of n log n. So that's the amount of work we are doing in this recursion tree, and that's the value of this recurrence. That's the asymptotic value of this recurrence, right? We haven't found the exact value, we have found the asymptotic value. Now one more thing, I have written a very simple recurrence relation for simplicity, And this recurrence relation kind of belongs to merge sort, right? In merge sort, we make two recursive calls and then we do merge procedure, which takes theta n time. In practice, you might have C1n plus C2, and these C also might not be same, right? This might be say C1, right? C1n, and this might be C2, right? Because in the base case, you will have different amount of work, and in the other cases, you will have different amount of constant work, or you will have different constants here and there, right? So, but if you consider even C1, C2, and if you just rewrite these expressions, say we have C1n, C1n, till the C1n, C1n, C1n till the last time, at the end we have C2n, right? Let's say we have C2n. This is also going to be turning out to be theta n log n. You can notice, right? How many terms do we have? Floor of log n, right? Total terms are floor of log n plus 1, but if I do not consider the last level, then I have total floor of log n terms, right? And how much work I am doing at every level? I am doing C1n into floor of log n. I can say theta log n, right? Floor ceiling we can ignore. Plus I am doing at the last level, how much work I am doing? Plus C2n. And this is a lower order term. When we talk about asymptotic analysis, we can ignore the lower order term. So we can again say it's theta of n log n. For simplicity only, I considered C1 and C2 both, but when you analyze the actual algorithms, they would be having different values.